this one immediately. Ladies and gentlemen, we now begin our showcase session. The first session for today is a research showcase by the 4 recipients of the 2021 POPSIG Student Research Project Bursary, sponsored by Desmet Palestra Malaysia, Studirat Berhad, and Malaysian Audio Chemical Manufacturer Group MOMG.
Just to note that for this session, there won't be any Q&A. If you have any questions, please ask during the discussion forum after the coffee break. And a reminder to all speakers, each of you will have 15 minutes to present. We will ring a bell once at the last 5 minutes of your presentation and ring the bell twice at the end of your 15 minutes presentation.
All right, the first speaker for today is Brenda Lim Ai-Lian, a process engineer at ExxonMobil Malaysia. Brenda obtained bachelor in chemical engineering and master in engineering science from Universiti Tunku Abdul Rahman. Her presentation today is titled Synthesis of Carbon Nanoparticles from Oil Palm Empty Fruit Branch as Electro-catalyst from Energy Storage. Without further ado, I will pass the stage to Brenda Lim.
Good morning, everyone. I'm Brenda from Universiti Tunku Abdul Rahman. So this morning, I will briefly share on my research study on the synthesis of carbon nanoparticles from oil palm empty fruit branch as electro-catalyst for energy storage. So without further ado, let's begin with the background study. The increase of population and growth in technology had caused an increase in energy demand, as well as the depletion of resources and the emergence of environmental issues. So renewable energy source could be a way to mitigate this problem but however, it is unstable as it relies on the surrounding nature. So the energy storage technology can be used hand in hand with renewable energy sources to maintain the stability of voltage and frequency by collecting and storing the energy produced from renewable energy sources. Metal air battery, or NAD, is one type of energy storage technology and is known for its high theoretical energy density, convenience, and safety. Figure 1 shows the global energy storage market prediction, and it's observed to have been increasing until 2030, and which means that NAD will have a big presence in the future. So how does NAD work? NAD consists of a metal anode, electrolyte, and air cathode. During discharge, oxygen reduction reaction takes place whereby oxygen from the ambient atmosphere is being reduced at the air cathode, and the metal anode is being oxidized to form reversible metal oxide. However, during charging, oxygen evolution reaction takes place whereby the metal oxide separates when an electron is being charged in. So there's a lot of advantages to metal air batteries, such as the high theoretical energy density. It is also lightweight and compact, as it uses the oxygen from the air, which helps to significantly cut down the size and the weight. However, there are several disadvantages, such as the low cycle stability. It also succumbs to lifetime shortening if it's exposed to high temperature and humidity. And most importantly, it uses high-cost air cathode material. So the air cathode is the key component of metal air battery. The current material used are carbon nanotubes, platinum on carbon, ruthenium oxide, and iridium oxide. These materials are costly, limited, and not eco-friendly. So for an air cathode to have high performance, to perform well, it should have hierarchical core structure, which is a mixture of microcores and mesocores, as it increases the number of active sites and channeling for mass transfer. Secondly, it should also have good catalytic properties to enhance the rate of reaction. Biomass waste are unwanted plant-based and animal or human materials. Biomass waste are good precursors for carbon synthesis due to its low cost and sustainability. So every year, billions of tons of biomass waste were generated, and its usability are often neglected. So using biomass waste as a precursor could help to reduce the threat to the environment. Besides that, biomass waste also have unique structures, as each biomass waste has different compositions of carbohydrates and polysaccharides. The all palm anti-fruit bunch is 1/10 of biomass waste, and Malaysia is the second largest producer after Indonesia. So far, there are no studies done on the carbon synthesis from all palm anti-fruit bunch as an electro-catalyst material. So the aim of my study is to synthesize low-cost carbon nanoparticles from all palm anti-fruit bunch for the application as electro-catalyst material in energy storage, which is metal and battery. And the objectives are to develop a synthesis method of carbon nanoparticles from all palm anti-fruit bunch to characterize the physical chemical properties of the synthesized material, and lastly to study the effect of the synthesis parameters to the physical chemical properties of the material. Next is the methodology. The carbon synthesis consists of washing, drying, and grinding all palm anti-fruit bunch as a pre-treatment step before carbonization, activation through wet impregnation, heat treatment, washing, and drying to form a carbon sample. So the parameters studied are the impregnation time, activating agent dosage, carbonization time, and carbonization temperature. The characterization can be categorized into the physical characterization and chemical characterization. Physical characterization involves scanning electron microscopy, transmission electron microscopy, X-ray diffraction analysis, and Bronner and Taylor analysis. For the chemical characterization, energy dispersive, X-ray, and Fourier transform infrared spectroscopy was used. For the electrical conductivity test was carried out using the current sweep method from 1 to 15 milliampere using a potential state. The carbon electrode was formed by mixing carbon samples, carbon black, PTFE, and 1,3-propane diol to form a homogeneous place before being shaped into an electrode and dried. So the conductivity was calculated using the equations shown. Moving forward to the results, starting from SEM and TEM, through observation, it was observed that an increase in impregnation time and activating agent dosage increases the formation of uneven surface and porous structure. This is because impregnation time and activating agent dosage to be related to the cleavage activation. So increasing impregnation time increases the reaction time, whereas the activating agent dosage increases how much reaction can take place. On the other hand, carbonization time and temperature affects the particle size, whereby the increase in carbonization time and temperature decreases the particle size. So we can see from figure 6A to B, which represents the SEM results at different temperature. An increase in temperature decreases the size of the particle. For 800 degrees carbonization time, as shown in the TEM image here, it was able to achieve nano size. However, after the optimum temperature, the structure will tend to collapse due to over-carbonization. So this is why at 900 degrees, the pores were observed to have collapsed. Next is the Fourier transform infrared analysis. When you compare raw OPEFB and the synthesized carbon samples, it can be seen that it can be said that the absence of carboxylic CO double bond and the peak at alcohol CO and sulfate CC double bond drops, which indicated that the KOH reaction takes place. But when you compare 800 degrees and 900 degrees, 900 degrees has insignificant heat, which may be due to the increase in bond breaking and the removal of elemental contact. Next is the X-ray diffraction analysis. We will focus on the front part of this graph. So when you compare raw OPEFB and the carbonized sample, the loss in double peak here will be due to the decomposition of lignocellulosic properties. When we compare the 002 peak here, which line here, an increase in temperature would cause a shift to the right, which means that there is an increase in degree of disorder. But however, after 800 degrees, which is 900 degrees, the peak shifted back to the left, which means that there is a decrease in degree of disorder, which may be due to over decomposition. Not only that, samples carbonized at 800 degrees have a broader peak than the other samples, which means that it is amorphous, and amorphous are preferred as it provides better electron mobility. KLH disrupts the atomic arrangement, which facilitates the electron transfer. Last but not least, is the BET, EBS, and EC analysis, which is the electrical conductivity. So through observation, the specific surface area increases with impregnation time, carbonization temperature, carbonization time, and activating agent dosage. So after optimization and after the optimum parameters, the specific surface area tend to drop due to the collapse in particle, porous and carbon structure. Another finding is that the electrical conductivity increases with a similar trend to the specific surface area. So when we compare the electrical conductivity with the specific surface area and the nitrogen content at 400 and 500 degrees Celsius, the specific surface area increases slightly, but the nitrogen content drops, which causes the electrical conductivity to drop as well. As for 600 and 700 degrees, the specific surface area increases, but the nitrogen content drops as well. However, it causes the electrical conductivity to increase. So that means that EC is affected by both specific surface area and nitrogen content. How does nitrogen content affect the electrical conductivity? It is because nitrogen affects the nitrogen enhances the electrical conductivity through charge redistribution. So to say that from this study, the optimum electrical conductivity obtained was 11.53 Siemens per centimeter, which is quite comparable to the commercial material, which is dependent on carbon at 12.13 Siemens per centimeter. So the main observations from this study are the impregnation time and activating agent ratio affects the porosity through KLH activation. Overactivation would cause widening and fusing of porous structure, which is not good, which also decreases the specific surface area. Carbonization time and temperature affects the porosity and particle size by causing defect within the carbon structure. Overcarbonization causes a defect formation, which increases the pore size, and the decrease in size of the particle, as well as the increase in pores number, mainly hierarchical pores, increases the specific surface area. And lastly, the electrical conductivity are related to the specific surface area and nitrogen content. So this research hoped to bring impact to the metal air battery market, to bring it closer to commercialization, as well as to decrease the production costs in the future. It also hopes to enhance the awareness of increasing generation of palm oil waste, as well as the awareness of the capability of other palm oil components other than the palm oil itself, the palm oil fruit itself, as a raw material to synthesize useful biomass waste-derived materials. We hope to decrease the waste accumulation by increasing the usage of other palm oil components And hand in hand, we hope to improve the general value of palm oil plants in the economic sector. And lastly, we hope to help Malaysia to take a step closer to achieving zero waste policies and to sustain a competitive advantage in the palm oil sector. So there are more studies that can be done to improve this research, such as the enhancement of electrical conductivity of the synthesized carbon through deeper and broader study, and lastly, to experiment on other types of biomass, palm oil biomass waste as well. So the conclusion of this research is that the synthesis of low-cost electro-catalyst material with comparable efficiency with oil palm and leafy branch is successful. And it was found that the impregnation time and activating agent ratio affects the porosity through pH activation. And lastly, carbonization time and temperature affects the porosity and the particle size by causing defect within the carbon structure. So the optimal parameters to obtain the best electrical conductivity and nanoparticle are 6 hours of wet impregnation, 1 to 0.3 carbon to pH weight ratio, 60 minutes and 800 degrees of carbonization to obtain 11.53 Siemens centimeter electrical conductivity. Before ending this presentation or sharing, I would like to thank POPSIG and Utah for their financial support, as well as Dr. Steven, Dr. Park, and Dr. Sheep for their guidance. Thank you.